Today I shall discuss about the biasing of JFETs. The biasing is for the same purpose as I explained for the transistors. It is meant for operating the junction FET in the active region such that it works as an amplifier. When you apply an input signal, it works as an amplifier, amplifies the input signal and gives you a strong output signal. So for this purpose, biasing of the JFET is required. So this is similar to that of in the case of a transistor. So please look at this diagram. You have the junction FET here. It's an N-channel junction FET, and it has drain to source. Here you have the channel, and this is the gate which controls the channel characteristics. The characteristics are as shown here. So this is the output characteristics between ID and VDS, and this is the transfer characteristics between the input quantity VGS and the output quantity channel current. Now we operate the FET in a particular operating region. Say in this particular case, say we operate it at -2 volts of VGS and about say 4 milliamperes of ID, and VGS is equal to, let us say, 4 volts. So this is the operating point. The operating point or Q point, that is the quiescent point, is given as VDS and ID. So this is the quiescent point. Now there is another quantity, VGS. Well, VGS is not independent of VDS and ID. So once the VDS, let me write it as VDS Q to indicate the quiescent point, and this is IDQ. Now the VGS Q is obviously dependent on VDS Q and IDQ, and the relationship is known that it is IDQ is given by IDSS. That means this current, which is the drain current for gate to source voltage, that current multiplied by 1 minus VGS Q divided by VP whole square. So through this relationship, VGS Q and IDQ are related. So these are dependent quantities. Hence, if you specify VDS Q and IDQ, that is as good as specifying VGS Q also. Hence, VDS Q and IDQ is normally what is referred to as the quiescent point. Now the question is, how do you select the quiescent point? That means what particular VDS Q and IDQ you operate, and how do you design a circuit to yield these voltages and currents? So it is, the analysis is similar to that in the case of a transistor, with some difference, the difference being the characteristics. There is a characteristic difference between a JFET and a BJT. So because of this difference, the circuits differ to some extent. Okay, so let us see what kind of circuits can be used. Before going into the circuits, how do you select the quiescent point? As explained previously while discussing for the transistors, stability of the quiescent point and linearity of the characteristics, linearity of the amplification characteristics, not the device characteristics. Okay, so these two are the important criteria in selecting the Q point. Stability, I repeat, stability of the Q point, that is VDS Q and IDQ, with respect to device variations or against device variations and against the temperature variations. So these are, that is what stability, I meant by stability, and linearity is for the input signals. An input signal has to be reproduced as far as possible in the same form. except for an amplitude, a shift in the amplitude or a gain in the amplitude, the shape of the signal should be retained. So that's what is linearity. That's what linearity means, and we see that we select the Q point such that it is in the linear region of the characteristics. That means when a small signal is applied, you have a large signal of the same type, and that's possible when the amplification characteristics is nonlinear. So this is the criterion for selecting the linearity, point of linearity. I'll discuss further about it when I discuss about the amplifiers. Now, we have different circuits possible for the biasing the JFETs. Let us now look at the self-bias circuit. Before doing the self-bias circuit, let me discuss about the fixed bias circuit. In the fixed bias circuit, we operate the JFET so directly by applying some fixed biasing to it. So this is, it needs to be applied some gate potential, the gate junction has to be reverse biased with respect to the source. So we apply a source here. Using a source, we apply some bias here. And to the drain, so through a drain resistance which is responsible for, or which is required to get an output, amplified output. So we use a drain resistance and we apply another source. Through another source we bias the drain to source channel. So this is the fixed bias circuit. So we need coupling capacitors to isolate the DC on this side with the DC value of the source on this side. So we use coupling capacitors on the input side to apply the input signal here, and we use coupling capacitors on the output side also, so to take only the AC signal across it and blocking the DC simultaneously. So the objective of the coupling capacitors is to isolate the DC on either side, because for DC voltages they act like open circuits in steady state, whereas for steady state, I mean when you apply a step, for instance, in steady state it gives you it acts like an open circuit, whereas for alternating signals it offers very low impedance and the signals can be coupled to the other circuit. So this is the arrangement for input and output signals. Well, in between is the arrangement for biasing. Now under reverse bias, the gate current is equal to the reverse saturation current of a device, of a PN junction, and that current is negligible. As you know that that current is negligibly small. For all practical purposes, you can treat it as a 0 for particularly when you are talking about biasing. If that current is 0, so please note that the gate to source potential, if you look at this junction, you can find that the gate to source potential is equal to minus VGG itself, because so this potential is equal to, so this potential minus this potential, the gate to source, the drop across RG, and since the current is 0 for all practical purposes, the drop across RG is 0, hence VGS is equal to VGG minus VGG. So that means if you want to apply a VGS of minus 2 volts, you simply use a VGG of 2 volts. So the biasing design on the input side is as simple as that. Now once the VGS is given, from the transfer characteristics, we can decide for that particular VGSQ, we can decide what kind of ID or how much of IDQ can be obtained straight away from the transfer characteristics graphically. Well, it can also be computed once VGSQ is given. IDQ can be computed using this equation also. Once a device is given, IDSS is given and VP is given. The pinch off voltage is given, and the short circuit, I mean, for 0 VGS or the drain current when VGS is equal to 0, that is IDSS, is given. So once these two are given, for any VGSQ, you can determine IDQ using this equation. So you can either use, you can find out from the transfer characteristics or using the equations. So from from VGS, we can determine, or VGSQ, we can determine IDQ. Now, once the IDQ is known, if you apply Kirchhoff's voltage law to the output equation here, so you find that, so VDD is equal to RD into ID plus VDS, or if this is, since it is quiescent value, I am writing it as VDSQ. VDSQ plus RD into ID, because ID is the drain current, is equal to VDD. So now according to this equation, so this is number 1, from this is second step, this is the third step. From this equation, we can determine VDSQ as VDD minus RDID, or VDSQ as VDD minus RDID. Once the circuit RD is known, circuit is given, that means RD is known, and ID is computed from second step, IDQ. Therefore, we can determine VDSQ. So, analyzing the biasing circuit and getting the Q point is as simple as this. Now, as I explained earlier, while discussing about the transistors, the design problem is the reverse. In the design problem, you do the reverse calculations. That means given IDSQ and the VDSQ, IDQ and VDSQ, that means the Q point, we find out the values of the resistances and the supplies. So that's what you do in the design problem. Prior to designing the circuit, that means finding the values of the various parameters like RD and so on, selection of the Q point is a design step, and selection of a particular biasing circuit, fixed bias or self bias, okay, circuit is also a design step. And before that, selecting a particular junction FET, you have several manufacturers manufacturing different FETs, and therefore we have different FETs available in the market, which are meant for different kinds of functions. Some can be used as good amplifiers, some have very high output impedance, some have low output impedance, and so on. Now you have to select a particular FET for your application. Okay, that is also a design step. Well, as far as biasing design is concerned, it is simply the reverse operation here. So we select a VDD and VGG. First of all, we select VGG such that the drain current we want to operate it around, say, -2 volts. We -2 or minus plus 4 milliamperes. Then from the transfer characteristics of the selected FET, we find out the particular VGS that is required, and we use that, we use a source or supply whose value is equal to the same minus VGSQ here. And once that ID is given, you know up to what particular and the VDSQ is given. Okay, you have to select the supply and the resistance both, and you know the current as 4 milliamperes already in this particular example. Now you have multiple choices possible. One can go for, say, if this is 4 milliamperes and you want, say, 4 volts, This is 4 milliamperes. One can use a 8-volt source and 1K resistance. One can go for even 2K resistance and 12-volt source. You have different choices possible. So you have to choose you have to stick to a particular choice and then design complete the design. So design is as simple as that. Now this resistance here, this RG, what is its role? It doesn't have any role as far as biasing is concerned, because VGS is equal to minus VGG, because no current flows through this. Practically no current flows through this. But RG is required to see that the input alternating signals are not short circuited into the VGG, into the source. If you apply two different voltage sources, say something like V1t, it's a time function if the voltage source is a time function, signal source. And if you have another signal source, V2t, and if you connect them together, it is just short circuiting one voltage source to the other voltage source. If this is say 1 volt fixed and if this is 2 volts fixed, so this is getting short circuited by this. So 1 volt of signal, that is the difference between these two, is getting short circuited. Only when there is a resistance you can avoid shorting it, and this circuit now works with a current flowing in this direction as V2t minus V1t by the resistance R. Otherwise it gets shorted. Now to prevent the shorting of the input signal into VGG, this RG is provided here. So in this case also, the fixed bias circuit doesn't give you a stable operation. For instance, some manufacturer says that the transfer characteristics of the device is typically like this, but it varies between this characteristics and this characteristics. Why? Again, the reason is the inaccuracy in the manufacturing process. So because of that reason, if the same type of JFET is taken and the same manufacturer, same type number JFET is taken, so you will find that some JFETs have this transfer characteristics and some JFETs have this transfer characteristics. So that much variation is there. So if you buy a device from the market, you are not sure whether the characteristics is this or this or in between. But typically, the manufacturers give you a typical characteristic. That is most likely this is the characteristics. This is true with all kinds of equipment. If you buy a scooter, go to the market and buy a scooter, are you sure about how much of mileage it gives exactly? There is some manufacturing variation. The same thing is possible here also. Same thing happens here also. Because of this reason, the transfer characteristics have some wide variation. Now, if you want to operate it at 4 milliamperes, typically this is the voltage required. For some device, if the device has this characteristics, the voltage required would be something different, and if some other device, the voltage required will be something different. Because of this difference, you have some uncertainty regarding what the value of ID you get for a particular VGS. Therefore, this circuit gives you a wide variation with the device. I repeat it. If we use say minus 2 volts as VGS, if this is the characteristics applicable, so you will find that the collector current is of the order of 2 milliamperes in this particular characteristics. Now, if this happens to be the device, you will find that the collector current is say 5 milliamperes. How much is the variation? 2 to 5 milliamperes. So if this is the characteristics, it may be saturated also. The device may be this may be saturated. This is this 8 volts minus some 5 into this is 2K. Okay, this may be saturating the channel. Hence, the device may not be useful as an amplifier. Hence, the fixed bias circuit is doesn't have good stability as far as the device variations are concerned, and also stability is concerned. With temperature variations, the characteristics, the p-n junction characteristics varies, and as a result, and IC naught varies, and the channel pinch off or the depletion region width also varies, hence the characteristics vary.
So when you use GP, does that correspond to VGS equal to 0 for that particular?
Pardon?
When we use VP, pinch of voltage, does that correspond to VGS is equal to 0 for particular VGS which we use?
The question is, at VP, that is the pinch off voltage, what happens to the transfer characteristics? Now, when VGS is equal to minus VP, look at these characteristics, you find that ID is equal to 0. The channel current is, for all practical purposes, the channel current is 0 when you apply the pinch off voltage at the gate to source junction. When VGS is equal to minus VP, this is equal to, or VGS is equal to VP, you have the ID equal to 0 for all practical purposes. You find some leakage current passing through it, but this is 0 otherwise. For now, let us look for better circuits than the fixed bias circuit, and we have a self-bias circuit, self-bias configuration. Available, and this configuration is a stable configuration. It gives you a stable biasing point or stable quiescent point. The circuit is given as shown here. Similar to that of the transistor, we use a resistance, a source resistance with the source, and a drain resistance here. So like in the fixed bias case, and the gate to source and the gate side circuit is through a large gate resistance, and it is grounded here. And these coupling capacitors are for coupling the alternating signals and to provide DC isolation here also. Other than that, the biasing circuit is as shown here. So this RD is to provide a large signal output, and RS is to provide some gate to source reverse potential, and RG is to avoid shorting of the input signal into the ground. I repeat, this RD is provided for obtaining an amplified signal. After all, the output current is controlled by the input voltage, small input voltage, and now when the output voltage is passed through a resistance, you will get an amplified output. So for that purpose, this RD is provided, and this RS is provided to give you some negative gate to source potential, some required negative gate to source potential. RS is provided. Please note that this ID, the drain current, is equal to the source current. So you have ID flowing here also. ID into RS is the voltage drop here, and that voltage drop provides you the required gate to source reverse potential. So that's why RS is used. And RS is also being used as a feedback element to keep the quiescent point stable. And RG is provided, like in the fixed bias circuit case, to avoid shorting of the input signal into the ground. So that is the purpose of RG. And this is the cell bias configuration. One way of doing it. That means there are different cell bias circuits possible. One can use a voltage divider bias here, and then that is also a cell bias circuit. So now let us first analyze the circuit and then see how it can be used for the design also. Now on the input side, please note that before that, please note that when the gate to source potential is reverse biased, which is being done in this particular case, this drain current is equal to the source current with opposite sign. That means the same current flows throughout the channel, from VDD into RD into this device and into RS. Therefore, now if you apply the Kirchhoff's voltage law here, so you find that VGS equal to the voltage drop VGS plus ID into RS is equal to the voltage drop across this. And this voltage drop is 0 because for all practical purposes, under reverse bias, the current that flows into the gate is 0. Therefore, this voltage drop is 0. Hence, VGS is equal to minus ID into RS. This is the input side equation. This is our equation 1. Now the output side equation gives us another equation. So that is VDD is equal to RD ID plus RS into ID plus VDS. This is the second equation. Please note that purposefully I have dropped the notation now. I am no longer writing Q here, but it is understandable. What we are doing is for the Q point analysis. So these are the two equations to be solved. And what are the unknowns here? ID is one unknown and VDS is the other unknown. ID and VDS are the unknowns. That means VGS should be known. For that particular ID, VGS should be known. So otherwise, there is no way we can determine, we can solve these two equations. You have the third equation, that is the characteristics, the transfer characteristics, the equation that describes the transfer characteristics as VGS. This equation, IDQ is equal to IDSS into 1 minus VGSQ by VP whole square. So this equation is also to be used there to solve these two equations. Or alternatively, we can use the transfer characteristics to solve this equation. Now let us look at it, let us try to solve this graphically, this equation graphically, using the transfer characteristics. Now the transfer characteristics is between ID and VGS, as you know, and the characteristics is a square law characteristics, something like this, and this is IDSS. Now when we design, we take the typical characteristics out of the whole transfer characteristics. with all that variation, we take the typical characteristics because that is most likely characteristics for the device. Now with the typical characteristics, this is the relationship between VGS and ID. Now if you look at equation 1, this is also between VGS and ID. Now this equation and this equation, these two are to be solved to find out that the particular value of ID which you get in this particular circuit. Now if you plot this equation, let us solve it graphically, VGS versus ID, this is equation. So you will find that, so this equation is a straight line equation passing through the origin. With the slope of the equation being minus 1 by Rs. Slope is 1 minus 1 by Rs. Now, once Rs is given, we can draw an equation with that slope, and this is the operating point. So it means in this equation, according to this equation, if this is the particular VGS given Rs, if this is the particular VGS, this is the particular current, drain current. This is IDQ and this is the VGSQ. Once Rs is fixed and the device is fixed, so for that particular IDQ, you will get this particular VGSQ given Rs. So that can be determined according to this equation. And once IDQ is fixed from this equation, we can compute it from this. We can compute VDS by substituting it IDQ in this equation. ID or IDQ in this equation. Hence the Q point can be determined. Okay. Now alternatively, you can use this equation to obtain the relationship between VGSQ and IDQ. So this equation and equation 1 can be used to solve for IDQ and then substitute in the second equation to determine the Q point. So this is the self-bias configuration. Now how does the self-bias configuration improve the bias stability? It is because of this source resistance. Stability is far better than in the fixed bias circuit. When because of the difference in the transfer characteristics, if ID tries to increase, then the voltage drop across Rs increases. That means the reverse potential, gate to source reverse potential increases because VGS is equal to the voltage drop across this with opposite sign. So if ID increases, the reverse potential increases, and if reverse potential increases, ID decreases. Because of this feedback provided through this resistance Rs, the ID is maintained at a constant level with minor variations, with some negligible variation. So that is the advantage of a self-bias circuit. And what is responsible for it? The Rs is responsible for it, because by providing an Rs, we are seeing that we are reversing the gate to source potential by an additional amount, which is again proportional to the incremental in the drain current. So because of this is possible. So please note that it uses a single supply, VDD, and only 3 resistances. Now this can be further improved with a voltage divider bias. This circuit can be, the stability of the circuit can be further improved to some extent with voltage divider bias. Cell bias circuit, with voltage divider. It is also known as voltage divider biasing circuit, but actually it is a cell bias circuit with voltage divider included in it. So since it is also a cell bias circuit, naturally we use an RD and an RS. Now, instead of an RG here through an RG, instead of shorting this, what we do is we divide VDD by two different resistances, R1 and R2, and then apply it to the gate. In the previous circuit, that is the cell bias circuit, so there was no additional voltage drop here. Whatever was the voltage drop across RS, so that is the gate to source potential, reverse voltage potential. Here we are providing something more than this. Through this voltage divider, we are providing some fixed voltage here to the gate. Earlier, I repeat, gate was provided with zero bias. Source potential was of course increased through this arrangement, and therefore that was responsible for some reverse gate to source potential. But here the gate potential is maintained at some constant level instead of zero level. That is the only difference between this one and this circuit and the other circuit. For all practical purposes, this current is zero. As I have explained, the gate current is zero. Therefore, the potential at this point is, if I call it as Vg, so the potential at this point Vg is VDD into R2 by R1 plus R2, because no current flows through this, and this is an open circuit as far as DC is concerned. Therefore, this potential VDD is being divided between R1 and R2, and what you get here is VDD into R2 by R1 plus R2. That is this potential. It's not zero like in the previous case. And what is the source potential here with ID as the drain current? At source, the potential is ID into RS. Now gate to source potential is this voltage minus this voltage. So this is equal to the fixed voltage Vg, that means VDD into R2 by R1 plus R2 minus IDRS. Previously, VGS was minus IDRS itself, and through this arrangement we are providing an additional term here. That's the only difference. So it is not only guided by IDRS, it is also determined by some external potential also. That is the facility you are getting here. Now VDS can be more flexibly varied, VGS can be more flexibly varied with a constant term and the ID dependent term. So that is the advantage in the circuit. And the output side equation, this is, as I said, now equation 1 in this particular case. And the output side equation is the same equation. VDD is equal to that ID flows through RS and RD. So the total voltage drop is ID into RD plus ID and ID into RS. plus VDS. This is the output equation. Now, equation 1 can be solved with the help of the transfer characteristics graphically, or with the help of that equation describing the transfer characteristics and equation 1, we can solve for ID and VGS, and then substitute that ID here and determine VDS. So that's how you do this, solve this. Now in this particular case, graphically, so let us try to solve it graphically using this equation. Earlier equation was passing through the horizon because the equation was VGS is equal to minus RDS. In terms of VGS and ID, it is a straight line equation passing through the horizon. Now it is this equation, VGS is equal to this constant minus ID RS. That means when ID is equal to 0, so VGS is equal to this constant, which is some positive value. So that means now the characteristics will get shifted to, please note that the slope of the characteristics is still minus 1 by RS. Therefore now the same characteristics now shifts to a value which is that constant Vg, which is equal to VDD into R2 by R1 plus R2. So what is the additional advantage now? Now in this case, this is the Q point. So this is the particular VGS Q it gives. Definitely it is going to be less than the previous one, because the previous one was totally reverse biased by that ID and RS. Now you are applying some elevating the potential of gate by that VG amount. Therefore VGS would be less than that and ID would be larger than the previous one. Right? So how much is the deviation that is required depending on your Q point? So you provide that particular VG. So that is the difference. So this is how you analyze the Q point graphically on the input side. So that means draw this equation and the transfer characteristics. With the help of both, you find this ID, substitute that ID in the second equation and you get VDS. So Q point analysis is as simple as this. Alternatively, you can use the other equation, the transfer characteristics equation. Now the design problem is the reverse problem. So given the circuit, you have to find out RD, RS, R1 and R2. Given the circuit and the Q point, ID and VDS. You have more number of unknowns. Here you have more number of unknowns than the knowns, than the equations. How do you solve this equation? For instance, right, whenever you have more number of less number of equations, you choose one and solve the others. If that is giving you an absurd value, that it indicates that your choice is wrong. You change the choice and then again do the same. So here, please note that although you have two values R1 and R2, Vg is the only variable. So that means this is the only variable. So this potential, how do you provide that potential? How much is that? If this is 2 volts and this is 12 volts, say you need Vg of 2 volts and this is 12 volts. There are different ways of providing it. That means there should be a voltage drop of 10, should be a voltage drop of 2 volts. That means it can be a 5K and 1K. It can be 50K and 10K. It can be 25K and 5K. So different combinations are possible. You choose any combination and it works. So this is how the design has to be carried out. Any questions?